Hello everyone and welcome to our lecture today. So today what we're going to be doing is more calculus on parametric curves, and we're going to start by looking at one of the neat things that we can do with arc length, and that's get more general formulas describing more general geometric properties. Specifically, this is using what are called surfaces of revolution, or revolving the curve around one of the axes. And so recall that for a parametric curve, and we'll parameterize this as x is equal to f of t, y is equal to g of t for t in some interval from a to b. I'll do ta to tb just to avoid confusion a little bit later when we use angle for our parameterization. And then this is going to be where f prime and g prime are continuous and not simultaneously zero. Then we define the arc length as, say, LAB, which is the integral from TA to TB of the square root of f prime of some integration variable squared plus g prime squared. And this is the integral with respect to this integration variable. And I'm not writing t here, I'm using a different integration variable because I'm going to do something really important. So using this formula, we can actually get a general relationship between arc length and the parameter of our chosen of our curve. And this means that for any t in our interval of parameterization, such that t is between TA and TB, the arc length on the curve up to t is a function of t, and this is going to be the definite integral from TA to t of the square root of f prime of tau squared plus g prime of tau squared d tau. Alright, so this basically says that you can go up to any point on the curve and get the arc length up to that point if you can figure out this definite integral from a to t, or from ta to t. And this is a direct functional relationship between arc length and the parameter t. Very, very important physically and also in many applications. This is the arc length from the point x of ta, y of ta, so from this point to the point x of t, y of t. But as long as f prime and g prime are not simultaneously zero, this thing is always going to be positive, so this is actually always going to be an invertible function because arc length is always going to be increasing. So this is a very neat thing that we have. And we also have a direct relationship now between the derivative of this and the integrand right here. So you'll recall from the fundamental theorem of calculus that the t derivative of the integral from some a, or some ta, to t of any continuous function, we'll call it h of xi d xi. Well, from the first form of the fundamental theorem of calculus, this is going to be the same thing as the t derivative of the antiderivative of h at the upper bound minus the antiderivative at the lower bound. And then from the second form of the fundamental theorem of calculus, we're going to have that, right? Well, before we do that, this derivative is going to be h prime of t, which is the derivative of the antiderivative. Then the t derivative of h of ta is going to be 0 because h of ta is constant. So the second form of the fundamental theorem of calculus says that the antiderivative, or the derivative of the antiderivative, is going to be the same thing as this integrand evaluated at t. And this is in general, right, for a continuous function h. Add this entire thing will just be equal to h with the upper bound plugged in. So what this is telling us is that the rate of change of arc length with respect to time, or ds dt, the derivative of this integral with respect to t, is going to be the square root of f prime of t squared plus g prime of t squared. And so this is a very neat observation and connection. And what we can also note, right, is that if we look at now the integral from a to t of this square root of f prime of tau squared plus g prime of tau squared, this entire thing we can think of in the sense of a u substitution. This is the same thing as a ds. And so this is the same thing then as the integral from 0 to s of t of 1 ds. Because if we're measuring arc length from ta here, the initial arc length is 0 at the point ta, and then we're measuring out to s of t, and so we get s of t as the total arc length. So this makes a lot of sense. It's very, very cool. So what I want to do right now is go over a relatively simple example using the arc length formula again, just to kind of review a little bit and make sure that we're all kind of following along, since the lecture on arc length was 2 lectures ago. So recall that if I want to figure out the arc length of, say, a straight line segment, any straight line segment can be parameterized by the equations x of t is equal to m1t plus x naught, and y of t is equal to m2t plus y naught for t in some interval from a to b. Well, why is this? This is kind of a nice verification for us, a simple verification for us of why that first tangent formula that we showed before is working. in two lectures ago, and this was that dy dx is going to be equal to g prime of t over f prime of t, which is going to be just m2 over m1, which is constant if m1 is constant and m2 is constant, which they both are. So this is a constant m, and specifically we have that for t in this interval, if 0 is included in this interval, so let's assume that 0 is included in this interval, when t is equal to 0, we have that at x of 0 is equal to x naught, whatever that value is, and y of 0 is equal to y naught, whatever that value is, when you plug in 0 to these equations. So really, right, let's say that x naught, y naught is this value right here, this point on the axes. From TA to TB, this is parameterizing a straight line going through the beginning point which is going to be the first point on the line, f of TA, comma, g of TA, and the end point on the line, which is f of TA or TB, g of TB. And the point x naught, y naught is on the line. This line has slope m in the yx plane. So it's the line y equals m times x minus x naught plus y naught in the xy plane, where m was determined by the two original parameterizations. So this is really neat, and we can go through and get the arc length of a line, which we'll call L. Again, remember, this is just to, do a sanity check and kind of verify the arc length formula once again. S of T, so the arc length from TA to any point t on the line is going to be the integral from TA to t of the square root of f prime of t, f prime of tau squared plus g prime of tau squared d tau. And both f prime and g prime are relatively easy to evaluate. F prime of t is the derivative of x with respect to t, which is just going to be the constant m1, and g prime of t is going to be m2, because both of these are constant. So the arc length as a function of t for any value t in the interval from a to b, TA to tb, is going to be the integral from TA to t of the square root of m1 squared plus m2 squared d tau. This is a constant, so it can come out of the integral. This will be the square root of m1 squared plus m2 squared times t minus ta. Like I said before, if we call this distance right here L, we have that L should be equal to S of TB, which is exactly the square root of m1 squared plus m2 squared times TB minus TA. Which makes a lot of sense. Oh, why does this make a lot of sense? We want to kind of investigate this a little bit. Well, if we rewrite TB minus TA into the square root right here, this is the same thing as the square root of m1 times TB minus TA squared plus m2 times TB minus TA squared and from the Pythagorean theorem, right, we can very clearly see that this is making a lot of sense, because if I call this length right here L1, and this length right here L2, L is going to be the square root of L1 squared plus L2 squared. M1 times TB minus TA is exactly L1, and M2 times TB minus TA is exactly L2. So this is very neat, and this is going to prove useful in one of the next examples I do when I talk about surface area. So I think at this point we've seen that we can very nicely use this arc length formula to give us the arc length, and really this is just the same thing as integrating the function 1 with respect to the arc length s. And this also should beg the question, what happens if we integrate a different function with respect to arc length? So what happens if I integrate from 0 to s of t some other function, maybe L of s ds? What's going to happen here, and what is this going to mean physically? It turns out we can get a lot of very cool results. So I'm not going to focus on all of the possible geometric results that we're going to get here. Instead, I'm going to focus on one specific example application, which I think suffices to show what I'm talking about here. And this is the idea of computing the surface area of revolution around an axis. So suppose that we have a curve here, a parametric curve, x equals f of t, y equals g of t, from ta to tb. So this is our parameter that gives points on the curve. For any point on the curve, we can just kind of plug in, and the point on the curve will be exactly f of t, comma, g of t, for any value of the parameter. So what I want you to think about is what shape you get if you symmetrically rotate this curve around an axis. We'll take the x-axis, for example, first, and then we'll move to the y-axis. But if you sort of symmetrically rotate this curve around an axis like this, and if you think about it for a little bit, it makes sense that what you're going to get is a nice surface that has a boundary of this curve, or a shape like this curve. And the whole idea of the surface area of revolution is finding a formula for the surface area of such an object. Now, in your Calc 2 class, you hopefully saw a formula for surface area of revolution of a function of x. This is going to be a little bit more general because it's going to be for a general parametric curve. Hopefully you saw the Riemann sum process for the formula that you saw in your Calc 2 course. If not, that's okay, but I'm not going to go over the direct Riemann sums here. I'm going to go over a more kind of general, nice idea that we can use to obtain the value that we're looking for. So the idea here is that at any point t in our parameterization, we're going to have a corresponding point x of t, which is the f of t, or x of t. It's this point right here. Just the x coordinate of this point on the curve. And the shape that we get when we revolve around this axis, right, this shape for any point on the curve is going to be a circle. So the idea here is that at every point x what the circumference of this circle is going to be. The height here is going to be y equals g of t. That's the y coordinate of this point in the xy plane. And so the circumference of this circle at t is going to be the circumference of a circle of radius r equals g of t. Now it's important that I also make some assumptions here about our curve. Right? I don't want to have the curve looping down into the negative y plane, and I don't want to have the curve repeating itself at all. Otherwise I'm going to be double counting the area. So in order to get the formula that I'm about to derive, we need to have y is greater than or equal to 0, and on this interval t from ta to tb, the curve does not repeat itself. Or in other words, every point on the curve are traversed exactly once. So as long as we have that, so the circumference of this circle is going to be 2 pi times r, or 2 pi times g of t. Because remember, the radius of this circle at some point t is just going to be the y coordinate of that point which is going to be exactly g of t. And so the value that we want, the surface area of the surface of revolution, is going to be the definite integral from 0 to s at tb, which is just the arc length we've traversed from this point to this point. It's the integral from 0 to s of tb of the circumference 2 pi times y of s ds. Which is the accumulation of the circumference function at every single point along this curve. So we're kind of like, you can think of it as like infinitesimally adding up the circumference at every single point along this curve. Now this formula can definitely be derived via Riemann sums. It's a very, very nice derivation, but it's a little bit long, so I just wanted to kind of go through this method of getting the formula, which is a nice intuitive method of thinking about what we're doing here. But in terms of practically evaluating this, we have to use the parameterization. So the formula does become a little bit longer. This is going to become the integral from ta to tb in terms of our parameterization of 2 pi times g of t, and ds, like we mentioned at the beginning of lecture, is the square root of f prime of t squared plus g prime of t squared dt. And so this is it. This is the formula that we need to evaluate if we want to find the surface area of a general region. And our conditions are met. So y is greater than or equal to 0, and the points in the curve are traversed exactly once. So I want to go through and show a couple different examples of applying this formula. The first one's going to be relatively simple. This is going to be the example of a straight line of slope m. So just like before, assume that we have the parametric equations of a line. X is equal to m1t plus x naught, and y is equal to m2t plus y naught. This is our f of t. This is our g of t. And we showed before why this is the correct parametric representation of a straight line. And if we consider the surface of revolution that we get when we revolve this straight line around the origin, again, we're going to assume that this is strictly over the y-axis here, right? So when we revolve it, we get a shape that looks like this. This shape is called a frustum. Of a cone. Really just a segment of a cone. But what we want to do is see if the surface area formula that we get is giving us the correct surface area of this frustum, geometrically speaking, what we would expect. And as you can expect, it definitely is giving us the correct result. It's relatively straightforward to show. We have that the surface area of revolution of this shape is going to be equal to the integral from TA to TB, where TA is the parameter of the beginning point of this curve, this line, and TB is the parameter of the endpoint of this line. So the surface area of revolution will be 2 pi times g of t times the square root of f prime of t squared plus g prime of t squared dt. This becomes 2 pi f prime is m1 and g prime is m2, both of which are constant. M1 is the linear rate of change along x, and M2 is the linear rate of change in the y direction. So this is going to be, the entire term right here is going to be constant. It's just the square root of M1 squared plus M2 squared. And then, so the last thing that we have here is g of t, which is exactly m2 times t plus y naught. Which is a relatively easy integral to evaluate. This is 2 pi square root of m1 squared plus m2 squared times m2t squared over 2 plus y naught times t. From an upper bound of tb to a lower bound of ta. So we have that this is going to be 2 pi times the square root of m1 squared plus m2 squared times m2 times tb squared minus ta squared plus y naught times tb minus ta, which admittedly looks a little bit complicated. But there are quite a few simplifications that we can apply to get a very standard, nice geometric formula that can be derived using other methods, other means. So this is very, very neat. The main idea is that tb squared minus ta squared will be tb minus ta times tb plus ta. So we can factor out tb minus ta from this whole expression right here. I'm going to rearrange some of the terms in the multiplication to give me something pretty nice. We got 2 pi times m2. Oh, I need a division by 2 here. Sorry about that. I dropped the division by 2 from this step to this step. It'll be m2 times tb plus ta over 2 plus y naught all times the square root of m1 squared plus m2 squared times tb minus ta. And the first thing that we notice, and this is from the arc length example, is that for that straight line, this is exactly the arc length L of the line, or just the length of this portion right here of the line from the previous arc length example. So this quantity is very simple, and this quantity is also pretty simple, especially if we rewrite this a little bit just to get an idea of what it's saying. This is the same thing as 2 pi times m2 times ta plus y naught plus 2 pi times m2 times tb plus y naught over 2 times L, remember, because this entire thing is L. And this is nothing but the average of the circumference of the beginning circle at TA and the ending circle at TB. And this right here is a classic formula that you can derive directly from the formula for surface area of a cone. Specifically, if you look at the frustum shape, you look at a cone, the frustum will always be the area of the surface area of this larger cone minus the surface area of a smaller cone circumscribed onto the surface of the larger cone. So if we take the larger cone and we subtract out the area of the smaller cone, what we're left with is the area of the surface area of this frustum shape. So this surface area right here. This is a classic formula. And just in the picture up here, C1 is the circumference of the larger outer circle, and C2 is the circumference of the smaller circle. So this is a very neat formula that comes directly from our surface area of integration, or surface area of revolution formula. And what I want to do now is go over a slightly more complicated example. And this is just so that we can see that sometimes, just like with the arc length problems, sometimes these surface area problems can also give us relatively tricky integrals to evaluate. So the curve that I'm going to take is the cardioid. I'm going to consider the surface area of revolution for the cardioid. Specifically, this is going to be the curve with r of theta, or r of t, given by 1 minus cosine of t. I guess I'll use theta just to really emphasize the polar coordinates here. And this is a polar defined curve. So x is equal to 1 minus cosine theta times cosine theta. Y is 1 minus cosine theta times sine of theta. And we need to go through and do the integral of the surface area formula. For the surface area formula from theta, or for theta from 0 to pi, or for really half of the standard cardioid. And the reasoning here is specifically because of the shape of the cardioid and the fact that this is the region for theta from 0 to pi where the cardioid has a positive value of y. And remember that when we derived our surface area formula, this is one of the big things that we needed to hold true. So I'll draw a little picture here just to kind of show what's going on. So you remember that theta equals 0, cosine of theta is 0, or so cosine of 0 is 1, cosine of 0 is 1, so 1 minus 1 is 0, and sine of 0 is also 0. So it kind of comes out and looks sort of like this, with a starting point at 0 and an ending point here. If we continued from 0 to 2 pi, it would finish the shape of the cardioid, but the problem with this is that we would be double counting the area if we included that entire from range from 0 to 2 pi. So we don't want to do that. And I want to directly show what's going on here, right? So this right here is our cardioid. It's the cardioid from 0 to pi. Right, like I said, if I went all the way to 2 pi, we would get the full cardioid. But the problem with that, and the problem in general, with going into negative y with your curve, is that when you form the surface of revolution, you end up double counting the total area if the curve is symmetric like this. Right, so it's really not something that you want to do, and you can see why we're double counting the area. We're kind of going over it twice with this section and this section. So this is why we got to be really careful and have y just be positive here. So I'm going to set the end bound just back to pi. We'll watch again the cardioid kind of fully revolve around the x-axis. And so in this problem, the value that we're going to be computing is the surface area of this shape in 3 dimensions. And what's kind of neat about it is you can think of it as almost like the perfect apple, right? A cardioid is like or the surface of revolution generated by the cardioid is kind of like an apple, because it has that location right here, which is a perfect spot for the stem of the apple. So you can think of the value that we're going to be calculating now as the total amount of skin on an apple, the area of the skin on a perfect mathematical apple. Specifically, if you were to say FOIL this entire thing out, the square root, and I went through, did this for you so you don't have to, you get sine to the 4th of theta plus sine squared of theta plus cosine to the fourth of theta minus 2 cosine cubed of theta plus cosine squared of theta and I think I'm going to need a little bit more space here. Plus 2 sine squared of theta times cosine squared of theta minus 2 sine squared of theta times cosine of theta, which is also very, very long. It's even longer than the form that we're starting with here. So this is not something that we necessarily want to integrate, but if we want to find the surface area of the cardioid, we're going to have to deal with this somehow. And sure enough, this actually does simplify very, very nicely using some factorizations, some trig identities, and some just general simplification. I'm not going to go through the trigonometry on this. You can see a couple simplifications that you get for free here. The sine squared plus cosine squared is going to be 1, but there's a couple other nice things like that we can do here. And believe it or not, this entire thing under the square root simplifies to just 2 minus 2 cosine of theta. And be a good exercise to go through and show that. But I don't want to waste the lecture time doing that right now. I just want to show you the calculus of what we're doing here. So essentially the idea here is, right, we've shown that square root of f prime of theta squared plus g prime of theta squared is 2 minus 2 cosine theta. And we want to now go through and solve for the surface area of revolution of this surface. It's going to be the integral from 0 to pi of 2 pi times g of theta times the square root of f prime of theta squared plus g prime of theta d theta from our formula. This is going to be the integral from 0 to pi of 2 pi times 1 minus cosine theta times sine theta, because this is our g of theta, remember, times the square root of 2 minus 2 cosine of theta. So I can factor out a couple things here. I have 2 pi that I can pull out. I also have a 2 that I can factor out of both of these terms, so I'll get a square root of 2 on the outside. 2 root 2 times pi times the integral from 0 to pi of, when I factor out the 2 here and pull the root 2 out, I get 1 minus cosine theta times the square root of 1 minus cosine theta, or 1 minus cosine theta to the 1/2 times sine of theta d theta. So initially a problem that looked slightly difficult is now appearing to be more and more straightforward, because when we simplify this, 1 minus cosine theta times 1 minus cosine theta to the 1/2 is going to be 1 minus cosine theta to the 3/2 times sine of theta. And what this means is that we can do a direct u substitution of u is equal to 1 minus cosine theta. So du will be equal to the derivative of this, d theta, which is going to be sine of theta d theta. And remember, u at theta equals 0 will be 1 minus cosine of 0, which is 1 minus 1, or 0. And u at pi will be 1 minus cosine of pi, or 1 minus negative 1, which is 2. So the surface area of revolution of the cardioid is going to be 2 square root of 2 times pi times the integral from 0 to 2 of u to the 3/2 du, which is 2 times the square root of 2 times pi u to the 5/2 over 5/2 evaluated at 2, evaluated at 0. The surface area of revolution of the cardioid will simplify to 2 times 2 is 4. You have 4 square root of 2 over 5 times pi times 2 to the 5/2. And 2 to the 5/2 is the same thing as 4 times the square root of 2. So when we plug in and simplify, you get the square root of 2 times the square root of 2, which is 2. 4 times 4 is 16. And so we get that the final value that we're looking for is 32 over 5 times pi. And this is the surface area of revolution of the cardioid. That's the thing that we're looking for. Right, the units of this are units of length squared in whatever unit of length that you're measuring in. So it's a little bit long, but it was definitely worth it, and a very neat example, I think, to show how to use this formula in a more complicated situation. But that will be all for the lecture. Thank you very much for tuning in. I hope you have a fantastic day and that you learned something.